Okay, hello everyone. This video will be about electrochemistry. So this has two parts. The first is electrolytic conduction and the next part is about galvanic cells. So we'll start off at this first part. So the basic thing is that in electrolytic conductions you have the ions in solutions moving and that causes current. So ions in dielectric liquid polarize the surrounding liquid to form a sphere of polar molecules attracted to the ion. Let's call the radius of this sphere as capital R. So as you can see in the figure over here, you have a positively charged ion and it is attracting these dipole molecules, and they are turning in or out depending on the field, and they align themselves causing this sphere thing which moves with the ion. Okay, a sphere moving in viscous fluid experiences a drag force given by Stokes' theorem as 6 pi r eta v, where r is the radius, eta is the coefficient of viscosity, and v is the speed. So the same thing will be for this sphere, so the red part basically. The force experienced by the hydrated ion due to an external electric field as measured in the dielectric. So the field due to your potential difference between the two plates where your ions are moving or anything like that, right? So basically the electric field at a certain point, right, where the ions are moving, and that too measured in the dielectric. So it's not the field that you would calculate for the case when there is no dielectric and it's just atmosphere. No, instead you have to divide by the dielectric constant and get this thing, right? So that is our electric field that we're talking about. So EZE will be the force on these red ions because of that external electric field, but then there's also the viscous force. So the net force is EZE minus 6 pi r eta v. So whenever this force becomes 0, that is when these ions or these hydrated ions, those start going at terminal velocity. That is also called the drift velocity, and equating this force to 0, you just get the drift velocity in that way. So our drift velocity is just EZE upon 6 pi r eta. Now we can call EZE upon 6 pi r eta as mu, Ez upon 6 pi r eta. So not with the capital E, just Ez upon 6 pi r eta. That is mu. Then our ionic, that's called ionic mobility. Then our drift velocity can be written like this thing: mu times the electric field. So basically the ionic mobility is just the drift velocity upon the electric field, and this remains a constant for any charge species, for that specific charge species, by the way. Okay, now consider this. You have a cylinder. This cylinder is filled with solution containing a species of ions with concentration m in molarity, of course. How many of these ions pass through the imaginary surface of area A as shown in the drawing in a time t? So the length over here is just Vd times t, so the velocity times the time required, and the area of cross section is A. So the volume that passed through is just the velocity times the area of cross section. So that volume contains the molarity times the volume amount of moles, but that would mean Avogadro's number times molarity times volume, those many charged species, which means, well, Z times of that is the amount of charge in terms of how many electrons, or the opposite of electrons, you could say, so how many of that is passing through. So basically the charge passing through it will be given by this thing. So this thing Z, Avogadro's number, molarity, the volume, but now that times small e, which is the charge of an electron without the sign, of course. So if I divide this Q by T, that will just give us the current. So the current is just Z small e, Avogadro's number, molarity, drift velocity times the area of cross section. Let's call the small e times Avogadro's number thing as Faraday's constant. So that is defined as Faraday's constant. We call it as F, capital F. Then the current can be written in this way. It's just ZF MA VD. But wait, we know that the drift velocity is just mu times E, right? And also that E times small l is equal to delta V. So delta V is just the potential difference across that electrolytic cell, and L is the length of the cell. So you can finally write our current as this thing. So now if we consider multiple ionic species, then the net current will just be the sum of contributions because of each ionic species. Also, you have to consider the fact that even if the charged species is negatively charged, it still carries the current in the same direction because it moves in the opposite direction, right? Okay, so you have this equation, capital I, that's our net current. That's just the potential difference times the area upon length times this sum, the molarity times this constant, the Faraday's constant times Zi mu I. I'm saying it's a constant because it does not depend on the molarity. It's only dependent on the species itself. So we can call this constant as the molar ionic conductivity because that's the contribution because of some particular species divided by its molarity, right? Contribution in what, by the way? First of all, we should tell that. Okay, so I upon delta V, that is the conductance, which is 1 upon the resistance, and L upon A times the conductance, that's the conductivity. So the contribution in conductivity because of a particular charge species, that divided by its molarity, that's the molar ionic conductivity. Makes sense, right? Okay, just read this terminology. There's nothing to explain over here. Note it down because you might need it later. Anyway, so now that we have noted it down, we'll move on. For an electrolyte, that is a neutral electrolyte, we define the molar conductivity as, once again, the same definition, just have the conductivity or the contribution in conductivity because of that, and that divided by the molarity. But since it's the only species we are talking about, we'll just say the conductivity itself. So the conductivity is, of course, is I upon delta V times L upon A, right? Capital M is the apparent molarity of electrolyte. So it's different from the actual molarity in this way that suppose we are talking about a salt which doesn't get solvated throughout, so like it reaches saturation and it now cannot dissolve anymore. So for that salt, we'll still take capital M to be the molarity that we would assume it will have if it completely dissociated, it completely dissolved, right? So that will be the number of moles put in upon the volume solution, not the number of moles dissolved or the number of moles dissociated into ions. No, it's the number of moles put in initially, which means that for weak electrolytes you could have your apparent molarity and the actual molarity as two different things, which we'll talk about later. Okay, so for now, consider this electrolyte dissolving like this. You have our electrolyte A that's dissolving into these charged species A1, A2, so on, and the stoichiometric coefficients are small a1, small a2, so on. The molarities of these species, well, those will just be the stoichiometric coefficient times the initial molarity of this guy, and that is assuming this completely dissociates. So for the final state, this will be happening. For a very dilute solution, every electrolyte does dissociate completely. So we can just say that the net conductance or net conductivity, that will just be the contribution, the sum of the contribution because of these charged species. So the first one contributes its molar conductivity, so lambda 1, that times its molarity, which is just A1M, and similarly for all of the other species. And the conductivity because of our capital A, right? So what we assumed was that the conductivity can be given in this way, the molar conductivity, by the way. Yeah, the molar conductivity is given by this formula, but that just means like m lambda. So this thing is capital lambda, by the way. Capital M, capital lambda, that's just L upon A, I upon delta V, which is, yeah, well, that's just the conductivity without the molar stuff going on. Okay, so yeah, I mean that thing is the same, right? LHS equal to RHS because both represent conductivity anyway. Your capital lambda is defined in such a way that this thing has to be conductivity, which means you can cancel off these capital M's over here, just get capital lambda equal to A1 lambda 1 plus A2 lambda 2, so on. This is called the limiting molar conductivity denoted by lambda naught. Why limiting? Because we considered very dilute solutions. So for different concentrations, you have different things going on. Well, that's for later part to discuss. But yeah, this is called the limiting molar conductivity, right? And for weak electrolytes, you don't actually have to worry about whether or not this conductivity is limiting or not, because it's yeah, I mean the thing is, the only effect that you have to take into account is that the dissociation may not be complete. So you will always be using limiting molar conductivity, and the actual conductivity that we'll be talking about, the molar conductivity, that you might have to report somewhere, right? Give an answer based on that. That will be calculated by this formula, of course. The apparent conductivity upon the apparent molarity. Yeah. So we'll talk about this later. First of all, this definition, I mean, it's not such a hard thing to consider. Okay, so till now we have not worried about the interaction of ions with the field produced by the other ions. So for weak electrolytes, we don't worry about that. We only worry about dissociation. But what if the field produced by the other ions affect how a certain ion is moving? So for a strong electrolyte, if we increase the concentration too much, these effects can't be ignored. So we have to use something called a Dieffenbach-Huckel theory. I don't know what this is. But what that says is that for a strong electrolyte, your molar conductivity is given by this formula. It's just lambda naught minus a square root of m. So m is of course the molarity, a is some constant, which is, yeah, just some constant independent of the molarity, and lambda naught is of course the limiting molar conductivity. The concentration effects on capital lambda for weak electrolytes are not because of interaction of an ion with other ions fields, but instead it's because of incomplete dissociation, as I already told you. So consider this thing: you have the same thing, the same neutral species, but now it's only partially dissociating. So initially it was just capital M molarity, but now after dissociation, let's just say its degree of dissociation is alpha, then its molarity will now be capital M times 1 minus alpha, and then A1 that will have molarity of small a1 times capital M times alpha, and then A2 will have small a2 times capital M times alpha, and so on, right? Because capital M times alpha is the amount that got dissociated, so that times the stoichiometric coefficients, that gives us this thing, whatever. So now our conductivity, which is capital M times capital lambda by definition, that will just be the sum of the contributions because of these guys, right? The neutral species, it does not contribute anything because it's neutral, and the charged species, so the first one is just A1 M alpha, that says molarity, that times the molar ionic conductivity, well, that's going to give us our contribution because of the first one. Then similarly for the second one, and so on. So you can once again get rid of these capital M things, just get capital lambda is equal to alpha times A1 lambda 1 plus A2 lambda 2, and so on, which basically means that lambda is equal to alpha times lambda naught. So using conductivity measurements, you can actually figure out alpha for different concentrations of some particular some particular electrolyte, right? Weak electrolyte, of course. Okay, now there is a thing that you have to be considering though, that H plus and OH minus, well, they don't move in this way that I just showed, right? They don't actually move in this way. Instead they move at a much faster pace. Why is that? That is because of this mechanism. I won't pronounce its name because I don't know how to. Okay, so the mechanism was like this: you have protons being transferred between our H2O molecules, and that means that they can basically like jump from one place to another, right? So usually what would happen is that some charged species would be blocked by what's in front of it, but then protons kind of teleport because, well, they are not blocked basically. They instead use what's in front of them, and then they move much faster. Similarly, OH minus moves much faster because of proton transfers. It's similar to this mechanism, except that the OH minus is created because of proton loss from H2O, so that creates an OH minus, and then the next H2O loses its proton to this OH minus, creating OH minus at that position, and you get that. It's like the whole moving, if that makes sense. Yeah, anyway, so this was about electrolytic conduction. Hopefully you understood what I thought you will, right? If there are any doubts about this, you can ask in the comments. Anyway, so this part is done. We are now finally going to this part, which is about galvanic cells and EMF due to reactions. So first of all, a very small setup. You have this half cell thing, which is basically just solid copper, so copper metal basically, and CuCl2 solution. Initially both parts are neutral, but because Cu2 plus can get attached to the solid copper through metallic bonds, this copper metal becomes positive and the solution becomes negative because Cl minus is in abundance now. This process stops after a while because the potential difference makes it non-spontaneous. So you can see you have these layers of charges being set up, and that causes a potential difference between this blue part and gray part, right? As you try to move a test charge from here to here, you will encounter a field in this very small section. Okay, so this process stops after a while where the potential difference makes it non-spontaneous. But we can't yet exploit this reaction to create electricity because unlike copper, copper metal, which can freely accept electrons, chlorine can't give its electrons just like that. So to allow this to happen, we use a platinum electrode. So what do I mean by chlorine can't give it? Well, if you attach some metal to it, what will happen is that for it to get rid of, right, so for chlorine to give its electron, it has to become chlorine radical, and then these chlorine radicals would bunch up to become chlorine gas. But then where would this gas go, right? So you can't just add wires on both sides and then say that we are done, we now have a source of voltage or current or whatever. No, that's not thing, because where will chlorine go? And once you have a lot of this chlorine dissolved in the solution, yeah, everything becomes more complicated. So what we do instead is we have this container which contains chlorine gas, right? So it stores the chlorine gas, and then also there's a movable piston, so it's always at the same pressure, which will require for some thermodynamic things going on in the next few lines. But yeah, that's the main thing over here. And it could also be that they don't actually have this piston thing, and instead they just open it to atmosphere and let the chlorine gas go. Well, in that case as well, the chlorine gas, as it's moving out, it's being worked against by the atmospheric pressure, right? Yeah. Or I should say the partial pressure of chlorine in atmosphere. I think something like that, right? Whatever. So yeah, in the end, it's just constant pressure. That's what we care about. Okay. So, right, this process stops after a while when the potential difference makes it non-spontaneous. But we can't yet exploit this reaction to create electricity because unlike copper, which can freely accept electrons, chlorine can't give its electrons just like that. So to allow this to happen, we use a platinum electrode and a container for Cl2 evolved with a movable piston. And we have this condition that our external pressure is just the atmospheric pressure or some pressure that's constant. Anyway, this setup is a complete voltaic cell. So I told you that this thing is just a half cell, well, because it's only having a single interface, right? So over here you have two interfaces, one with copper and this solution, and over here you have the solution and the platinum. So you need two electrodes, and over here you only have one electrode, one metallic part. You have two metallic parts over here. So it's a complete cell now. A lot of the times you will also have salt bridges and different electrolytes. Yeah, that might be there, but I'm not drawing all that because yeah, well, this is simple enough to understand, I think, right? And also accurate enough. Okay, so usually a cell refers to setups like this, where we have two electrodes, as I told you, and one or two electrolytes with a salt bridge between them. So in case of just one electrolyte, there's no need, but then you have two electrolytes, sometimes you need salt bridge between them to transfer the ions without really physically transferring them. You will see what I mean when you will learn about salt bridges. Okay, the reactions creating EMFs are, so first you have the reaction on cathode going on, which is basically just CO2 plus getting attached to this copper metal and becoming copper, like a part of that metal. So that reaction as a whole is just this thing, Cu2 plus 2 electrons, that gives copper. So let's just say that this reaction gives free energy delta G1, and anode you have this reaction going on, so 2 chlorine, so 2 chlorides, sorry, that just becomes chlorine gas, and they give off 2 electrons, and that has delta G2 as its gives free energy. Then you can add these two reactions to present the final reaction that is occurring in this cell, right? So over time, this is the reaction that you will see. So you just have Cu2 plus 2Cl minus, that's giving copper plus Cl2. and this has of course the Gibbs free energy as delta G1 plus delta G2. Since the system is at constant pressure temperature, we can use our delta G, which is delta G1 plus delta G2, so the final Gibbs free energy for the complete reaction, that as the measure of spontaneity. So remember something, that for a process at equilibrium at constant pressure temperature, you need delta G equal to non-PV work, right? That's the measure of spontaneity over here actually. Okay, in our case, work done non-PV is because of the wire transferring electrons from our system cell through a potential difference E. So in the last section we saw that E was electric field. Here I'm using it as the potential difference, not that much of a hindrance I would say, right? Because it's used as E everywhere. So okay, so what's happening is that this wire is taking electrons from the part where you have chlorine, right? Okay, it's taking electrons from platinum and it's moving it to copper, right? But that means it's actually moving it through a potential difference, and that that causes negative work to be done on this cell of ours. So when I say cell, I mean just the part without the wire, right? So the wire and the resistor, that is a part of surrounding, and then this gas, this piston, and yeah, this shaded part, so the copper and platinum and the electrolyte in between, that's our system. Okay, so for equilibrium, just have delta G equal to non-PV work, and although I'm saying equilibrium, mostly you won't be having equilibrium, instead you will be having delta G not being equal to the PV work, right? But you can kind of assume that it is almost at equilibrium, right? Yeah, but it's okay to do that. So in our case, work done PV is because of the wire transfer, so wire transferring electrons from our system through a potential difference E. For every 1 mole extent of this reaction, n equal to 2 moles of electrons are transferred. So you have this final reaction going on. Whenever you have 1 mole extent of this reaction, every time you just have 2 electrons transferred whenever this reaction happens, right? So for 1 mole extent, you will have 2 mole electrons that were transferred through this wire. Okay, which means that n Faradays of charge is transferred. So n equal to 2 in this case. In general, you just have n moles of electrons being transferred, right? Okay. Yeah, so n Faradays of charge is transferred. Faraday's constantly, of course, no. So the work done non-PV, that is just negative NF times E, because E is the potential difference, negative NF is our charge, right? So delta G, that is work done non-PV, that's just equal to negative NFE for equilibrium. Now you might be having some problems with where exactly is equilibrium over here. Well, this is not actually what's going to happen in practice when you will be using this on some resistor. No, this is actually basically saying that if you put another cell or something that that has the potential difference given by this formula, so basically delta G upon negative NF, right? That's our E thing. So if you set up another cell attached to this thing, then will current flow through that or not? Basically that's what it's going to tell us. And for quasi-static process, you can actually assume that it is almost at equilibrium throughout, because it's not very spontaneous, but well, whatever. Okay, so what was I doing? Right, we have proved while studying thermodynamics that for a reaction involving dilute solutions and gases, you can write delta G as RT natural log of Q upon K, where Q is the reaction quotient and K is the equilibrium constant, and both are calculated in the same way, right? That's an important thing. Both are calculated in the same way, and the usual way to do that is by taking some standard pressures and concentrations, right? And then figuring out in those units how much is our Q and how much is our K. So for example, you have, I don't know, like H2 1 atmosphere, let's just say 2 atmosphere. So you have 2 atmosphere H2, right? Or for this particular example, you might have this 2 atmosphere Cl2. Then you will just put 2 as our activity of Cl2 thing, because we'll just say that 1 atmosphere is the is the one that you will need for Q equal to 1, right? Okay. So you can write delta G equal to RT natural log of Q upon K, which is also just delta G naught plus RT natural log of Q. So here you might think, okay, but isn't Q supposed to be having units? Well, no, no, it doesn't. For thermodynamics, we always choose units according to which you have to write Q, and then we cut off those units. So basically, this is just a pure number. Q is just a pure number, right? And then delta G naught, that is just equal to negative RT natural log of K. So everything works out fine as long as you maintain your unit system. Okay. So then using this equation, you can write E is equal to negative RT upon NF natural log of Q upon K, which can be written as E naught minus RT upon NF natural log of Q. So E naught is of course the it's the standard potential because of this cell reaction going on. Okay. Standard reduction potential. Since we can only find delta G using delta G equal to negative NFE and not delta G1 and delta G2. So basically what's going on is that if you have E given to you, so you measured how much is our potential induced, then you can actually get what the delta G for this reaction should be for the complete cell reaction, but you can't get what delta G1 and delta G2 should be for these reactions, right? So you can't get those directly, but what if we set delta G1 or 2 to be a fixed thing, and then vary the other one, the other half cell reaction, and then we can actually compare, right? Because we'll have delta G1 plus delta G2, that thing varying, but we know that delta G1 does not vary, so basically it's delta G2 that is changing, and how much is that change? We can figure that out, right? Yeah. Okay, so since we can only find delta G using delta G equal to negative NFE and not delta G1 and delta G2 individually, we can set delta G to be a fixed value, just as I told you, right? And we can compare. I think this was supposed to be delta G1. Okay, we can set delta G1 to be a fixed value, and we can compare delta G2 for different reactions. To fix delta G1, we use the same half cell, which is the standard hydrogen electrode. There is also a different standard electrode that sometimes is used, right? But we'll not talk about that. We'll just use the standard hydrogen electrode as our reference. So we'll use this every time, yeah, and we'll use it as the anode, right? And when I say anode, I mean supposedly anode. It may not actually work as the anode all the time, but then we are assuming that it's gonna work as the anode, right? And yeah, assuming it's anode, and then we'll see in which way the current is flowing, in which way is the potential difference, right? We'll measure it in that sign convention. Anyway, so also we use the standard conditions for the other half cell, right? Because we want to compare reactions, and reactions can be at different delta G values at different temperatures, different pressures. So we'll just have the same pressure, same temperature, which will be the standard conditions. Yeah. Okay. The EMF measured is called the standard reduction potential for that reason. Now you might think, why is this useful? Why are we figuring out this EMF? Well, we can use this for comparison between tendencies of reduction for two different reactions. So for example, I don't know, reduction of chlorine gas versus bromine gas. How much is the tendency for chlorine gas? How much is the tendency for bromine gas? You can use that for chemistry reasons, and you can also use this for figuring out what will be the EMF of cell if you make it out of some particular half cells, right? So I'll show you an example. First, you have this thing, you have CuCl2 and Cu, this half cell, and you have SHE, which is standard hydrogen electrode. So these two half cells make up our cell, and the EMF thus measured will just be 0.337 volt approximately. So this basically means that delta G for this reaction, Cu2 plus H2 gives 2H plus Cu solid. That's our cell reaction. That is just negative 2 Fe1. Why 2? Because n equal to 2, right? So negative n Fe, over here just have negative 2 Fe. Okay, and in some other cell you have ZnCl2 and Zn and SHE, and the voltage thus produced will just be negative 0.762. So now what is this actually negative? What is this? What does negative actually mean? It means the voltage is reversed, but then its magnitude is just 0.762, right? Okay, and once again the same thing goes on, that delta G for this reaction, the cell reaction, it's actually not happening over here, the opposite is happening, but then whatever. So for this reaction, our delta G, which is just negative 2 Fe2 now, right, this will be positive because E2 is negative, which means that it's literally not happening, the reverse is happening, but whatever. We only care about the values and the maths, we don't actually care about what's happening physically. Yeah, the negative sign means that voltage is in opposite direction, of course, and delta G for Cu2 plus Zn gives Cu plus Zn2, so Zn2 plus 1. This now you can actually figure out because of these values. So that's just basically like this reaction minus this reaction, right? So yeah, the delta G for this reaction will just be the delta G of this reaction minus the delta G of this reaction, which is basically this thing, and that happens to be negative 2F times E1 minus E2. But you know that delta G for this reaction, right, that can be used to figure out the EMF of this cell. So for this cell, just have delta G equal to negative NFE, which basically means delta G upon negative NF, which in this case is just this thing, plus 2F times E1 minus E2 upon 2F. The negative became plus. Anyway, so this thing, that will be our cell EMF for this cell. Okay, and this is just E1 minus E2, which happens to be 1.099, approximately 1.1 volts, and that is the EMF for copper and zinc batteries. Right, and by the way, all of this is supposed to be under standard conditions, so this is actually supposed to be E1 standard, E2 standard, but whatever, right? And then you can use this equation. Where did that equation go? Right, so this equation is called the Nernst equation. I don't know how to pronounce that one. Right, so you can use this equation to figure out our E values for different concentrations, right? Because you already know what the standard value is going to be. Also, you need to know some values to actually use this effectively. So this can be written in this form: E is equal to E naught minus RT natural log 10 upon F times 1 upon n log base 10 of Q. Right, so RT natural log 10 upon F, that has the value 0.06 volts approximately. So basically we just get E is equal to E naught minus 0.06 volts upon N times log base 10 of Q. And of course, here this is supposed to be at room temperature. Right, so yeah, that's it. This was electrochemistry. Oh, also, I think I should tell you this. The delta G method, it might be slightly more lengthy than just, subtracting the EMFs, right, or adding the EMFs based on what's going on, right? So just, doing it the electrostatics way, that might be just easier because you have actually a physical thing going on. But then for reactions that are more abstract, that is for reduction and oxidation just given on page and we don't actually know what's physically happening, always go through delta G, right? So always convert your EMFs into delta G, and after you go through the thermodynamics, convert it back into EMFs, right? That way you will make less mistakes, I think. Yeah, so that's it. Okay then, so I'll see you guys in the next video. Okay, this is kind of weird. Okay then, I'll see you guys in the next video.